Hello and welcome. Today we shall first talk about some special signals and then we shall talk about systems. Let us begin. Let me first draw a signal whose value is equal to half within the region that time is greater than -1 and less than +1. After this time, the signal goes down to 0 and remains 0 forever after. Before time equal to -1, the signal was also 0. Now let me calculate the area under this curve or signal. And the area is given by the width of this curve, which is 2 unit multiplied by the height of this curve, which is half unit. So the area is 1 unit. Let me now draw another curve which is taller than this yellow curve, whose value is equal to 1. But this curve is also narrower than the yellow curve. So it goes down to 0 at time equal to half, and before time equal to -half it was also 0, and after this point this is again 0. Now the area under this green curve is given by the width of this curve, which is 1, multiplied by the height, which is also 1, so the area is 1. Next, I shall draw another curve which is even taller, whose value is equal to 2, but this is narrower than the previous two curves, which goes down to 0 at t equal to 1/4 and remains at 0 ever after, which is also 0 before the time t equal to -1/4, and only within this narrow region its height is 2. Now the area under this blue curve is equal to the width, which is half unit, multiplied by the height, which is 2 units, so the area is again 1. This way I can continue to draw signals which are taller and taller and taller than the previous signals, but at the same time they will be narrower or thinner than the previous signals. For example, I can define a signal, call it xt, which is 0 outside the region, say t equals plus epsilon and t equals minus epsilon. So between these two times, t equals plus epsilon and minus epsilon, the signal is non-zero, and outside the signal will be 0. Let me write it this way, that xt is equal to 1/2 epsilon if time is less than epsilon and is greater than -epsilon. Within this region, the height of the signal is 1/2 epsilon, but outside this region the height of the signal is 0. Now let the width of xt, which is same as 2 epsilon, be very small, or let it go close to 10 to 0. Under that situation, you can imagine a signal which is extremely narrow, but its height will also tend to infinity. So under that situation, the height, which is 1 over 2 epsilon, that tends to infinity. But no matter whatever value I choose for epsilon, the area under the curve xt will be equal to 2 epsilon multiplied by 1 by 2 epsilon, which is same as 1. So area is constant. However, as I change epsilon, the signal becomes narrower and narrower and narrower and taller and taller and taller. Now the extreme situation when epsilon tends to 0, that extreme signal that you can imagine is called an impulse signal or an unit impulse signal. Okay, now that we shall draw in this way. Let this be the time axis, and now that extreme signal is so small, so narrow that its value is 0 soon after time t equal to 0, and soon before time t equal to 0 the signal is again 0. Now within this very narrow region, its height will be very large, and so we shall draw it with a single line because it is very narrow. So we will use a single line, but we cannot draw an infinitely long line, so we shall put an arrow to denote that this signal goes or tends towards infinity. This is the symbol of an impulse function. This is time equal to 0. So this is the symbol of an impulse function, which is also called a delta function or delta signal, and is normally denoted with the Greek alphabet delta of time t. Mathematically, we shall define this function in this way. Delta t will have a value of 0 if time is greater than 0 plus. If time is slightly greater than 0, then the delta t will become 0. Its value will also be 0 if time is slightly less than the 0 or 0 minus. The value of the signal will be very high between this region 0 minus and 0 plus. However, the area under the curve, which is same as the integration of the signal delta t multiplied by dt from time equal to minus infinity to plus infinity. This integral gives the area under a curve. This is equal to 1. The signal is very narrow but very tall. So the area is neither zero, neither very large, but it's a finite number. And this is the mathematical definition of an impulse function or an unit impulse function. So this is called an unit impulse signal. Unit because the area under the signal is 1. An impulse function is slightly difficult to visualize or imagine, but now we shall look at some simpler functions. Unit step function or step signal. This is defined as follows. It is normally denoted with the letter U and its value is equal to 0 if time is less than 0 and its value is equal to 1 if time is greater than 0. That is the definition. Now let me draw this signal. If this is time axis, this is t equal to 0. If this point has a height of 1, then the value of ut is equal to 1 after time 0 and its value is equal to 0 before time 0. This is u of t. Let me define another simple signal which we call an unit ramp signal, which is defined in this way. R of t, R for ramp, is equal to 0 if time is less than 0 or less than equal to 0 and its value is same as t if time is greater than or equal to 0. Let me draw this ramp signal. So before time t equal to 0, the value of this signal is going to be 0, and after this point it will increase with a slope of 45 degree. So this signal is called R of t, ramp signal or unit ramp signal. Now let me ask, how will the signal ddt, that is the time derivative of rt, will look like? So this is RT, and we want to find how the derivative, time derivative of RT will look like. Let me draw. Observe that before t equals 0, RT is constant, and therefore its derivative will also be 0. So before time equals 0, the derivative of ramp signal is 0. After time t equal to 0, RT increases with a constant slope. That slope is 1. So the derivative after t equal to 0 will be a constant equal to 1. So this is time versus ddt of RT. So you observe that this signal is same as the unit impulse signal. So this is a very useful result, that the derivative, time derivative of an unit ramp signal is same as the unit impulse signal. I can tell this in the other way. Suppose I calculate the integration of ut over time dt from time t equal to minus infinity to some point capital T, t equals capital T. What will be the result of this integration? Suppose the point capital T is here, then I am integrating this signal from minus infinity up to this point. So I am calculating the area under this curve from minus infinity to this point, and that area will be given by the height, which is 1, multiplied by the width, which is t. So 1 multiplied by t is t. However, if t is negative, that means this point is on the left side of the vertical axis, then the area under the curve up to that point will be 0. So the result of this integration is equal to 0 if t less than 0 and is equal to t if t is greater than 0. I can also put a greater than equal to or less than equal to. So do you notice that this is same as the definition of the ramp signal? So I can write that this is equal to R of t, capital T, because this is a function of capital T. Small t will cancel when you integrate, and this capital T will remain. So this is also a very useful result, that the integration of unit step function is same as the ramp function, and the opposite is also true. the derivative of ramp function is same as the unit step function. Now I shall ask the question that if I differentiate dt an unit step function, what shall I get? Let me draw the step function. You know its value is equal to 1 after the origin, and before the time t equal to 0 its value is equal to 0. This is ut as a function of time. Now we want to plot the function ddt of ut as a function of time. Note that before t equal to 0 ut is constant and therefore its derivative will also be equal to 0. After t equal to 0 ut is again constant, so here also the derivative will be 0. But at the point t equal to 0, what is the derivative? You may say that the derivative is undefined. But we can define the derivative in another way. Let us see that. What I shall do, I shall first approximate this signal in the following way. I shall draw an approximate ut, which is not ut, some approximate ut, and which looks like this. It is 0 before t equal to -1, and then it goes up slowly, gradually, linearly, and it becomes 1 at t equal to 1, and then it remains at that value. Now I can differentiate this approximate curve, and if I do that, ddt of approximate ut, that will have a value of 0 before this point because the function is constant. After t equal to 1, again the function is constant, so the derivative will be 0. And within this region it increases linearly, so the derivative will be the slope, and the slope is half, so its value will be like this. So this is the derivative of approximate ut. Now in the next step I shall do a better approximation of ut, which looks like this. It is 0 from -infinity up to this point t equal to -half, then it will go up gradually, and after t equal to half it will become 1. So this is t equal to half, and the derivative of this approximation will be as follows. It will be 0 from -infinity to minus half. After plus half it will be again 0, but within this region minus half to plus half it increases linearly and the slope is 1 unit. So that will look like this. This is 1 unit. This way I can keep drawing better and better approximation of ut, which goes up faster like this, and therefore the derivative will also look like constant before some point t equal to minus something, and after some point it will again be 0, but within that narrow region it will have a high value. Now I leave it to you to verify that the area under any of these curves, is equal to 1. This red curve or this green curve or the white curve, which are approximations of this derivative, all have constant area under them. And if I keep doing better and better approximation, you shall realize that the result is going to be narrower and narrower, taller and taller. However, the area shall remain constant equal to 1. And this is nothing but our unit impulse function. When you take the extreme limit, when you imagine the extreme limit, this is going to be our unit impulse function. So the result is that ddt of, let me write here, ddt of ut is equal to delta t. I can also ask the opposite question, that what is the value of this integration of delta t from time t equal to minus infinity to t equal to some constant capital T. How much is this? Let me draw the delta function. Time, this is t equals 0, and the delta function is denoted with an arrow. This is unit delta function, delta t. And if I integrate the area under this curve, then the result will be as follows. The result will be 0 if capital T is less than 0, because here delta T is constantly 0. However, if this time T is somewhere on the right side, then the area under the curve will be the area under this delta function, which is same as 1. That is by definition. So if t is greater than 0, then this integration result in 1, and if t, capital T is somewhere on this side, then the result will be 0. And you should now recognize that this is the definition of our ut. So this is again another important result, the derivative of ut is delta t and the integration of delta t is ut. This should be capital T. Okay, because this is a function of capital T and not of small t. Okay. At this point, I will just tell you a fact that previously I told integration of delta t from minus infinity to plus infinity, that is the total area under the curve, is equal to 1, but I can also write that the integration of delta t from t equals 0 minus to t equals 0 plus any number slightly greater than 0 and any number any number slightly less than 0 and any number slightly greater than 0. Between this region, if you do the integration, that will also be equal to 1. Okay, because the entire area is squeezed within this narrow region. Outside this, the area is anyway 0. This side area is again 0. So within this narrow region, the area is 1, and therefore the total area, which is this integration, that is also 1. Okay, let us now recall the definition of delta t, that delta t is equal to 0 if time is slightly greater or slightly less than 0, equivalently if time is not equal to 0. However, the area, which is the integration of minus infinity to plus infinity delta t dt is equal to 1. This is the definition of delta t. Now imagine another function yt, which is k times delta t. So this is amplitude scaling of delta t. What can we say about yt? We can say that yt is equal to 0 unless time is 0, because if t is not equal to 0, then delta t is 0. 0 multiplied by k is 0. However, the area under this curve yt dt from minus infinity to infinity, that is same as the area under k delta t dt, and since k is a constant, I can take k outside, and this integration is 1, therefore this is equal to k. To visualize this, you imagine that I plot time versus delta t, and delta t is a very narrow signal and very tall, and the area within this curve is 1 unit. This is delta t, whose area is 1. Now if I plot time versus k times delta t, then that will be k times taller than delta t, so it is more tall, and the height is increased by a factor of k. This is k delta t, and the area will be k times 1. Okay. Now let me ask a very important question. Suppose I define yt, a function which is xt, some other arbitrary function, multiplied by delta t. Then this is equal to what? Let me draw first some arbitrary signal, time versus some arbitrary signal which is like this. This is x of t, and let me also draw delta t on the same picture. So delta t is 0, and here delta t picks up. We denote that with an arrow, and then it comes down and becomes 0 again. This is delta t. Now if we take the product of these two signals, then the result will be, of course, 0 in this region because delta t is 0. In this region again the product will be 0, but at time t equal to 0 it is not 0. Let me zoom into this part. So if I zoom in, then I shall see a very tall signal delta t, very narrow, so this is delta t, and let me also draw xt. xt in this part within this small narrow region is fairly constant. This is xt zoomed in, and the height of xt at this point is same as x of 0. Now if you multiply these two signals, the product will look like delta t being multiplied by the constant x0. So the product will be taller than delta t, and therefore the area under this curve, which is delta t multiplied by x0, the area will be x0. So what we can say is that yt is a curve such that this is equal to 0 if t greater than 0 or if t less than 0, and the integration of yt or the area under this curve is equal to x0. This is a constant number, and therefore yt is very similar to delta t, but it is larger than delta t. So we can say that yt is x0 times larger than delta t. This is a very important result. Okay, I should rather write it here. this is same as x0 times delta t. Okay, and therefore as I said, x t delta t is same as x0, a constant number, multiplied by delta t. So it implies that the integration of xt multiplied by delta t from time t equals minus infinity to plus infinity dt will be same as x0 delta t integrated minus infinity to plus infinity dt, and this is same as x0 integration of delta t dt. Since x0 is a constant, I can take it outside the integration and the result is x0. So I can in fact also say that xt delta t, this integration, instead of taking it from minus infinity to infinity, I can also just integrate around the origin 0 minus to 0 plus, because that is where this signal is non-zero. So therefore the integration from 0 minus to 0 plus is same as the complete integration, and the result is equal to x of 0. So this result you must remember throughout your life or throughout the course. Next, let us define a signal, say yt is equal to delta t minus some constant t, capital T. So this is a constant. How will this signal look like? If you remember what we learned in our previous class, when you subtract some number from the time, the signal is shifted towards the right by an amount, this number capital T. So that signal should be drawn in this way. So this is how we draw. This is how we draw delta T. Now we shall shift this signal towards the right. So let me draw it somewhere here. This is going to be the shifted, time shifted delta t minus t. This point is t equal to t. Okay. Now let me ask another question. If I define a signal yt, which is some arbitrary signal xt multiplied by delta t minus t, and this capital T is a constant number given. Okay, for example, let me take this to be equal to say minus 5. How will this signal look like, or what will be the result? Let me first draw some arbitrary signal. let this be an arbitrary signal x of t, and delta t minus 5 will be here 1, 2, 3, 4, 5. At this point, this is delta t minus 5. The height of xt at this point can be written as x of 5. Now if you multiply xt and delta t minus 5, then the result will be, of course, 0 in this part, will also be 0 in this part, but will not be 0 at t equal to 5. And at t equal to 5, the product or yt will have some area under it, and the area under yt at or near t equals 5 will be x5, because this is the constant number which is being multiplied to the height of delta t. So therefore I can say that the product yt will also be an impulse function, and the area under yt is x5, therefore yt is x of 5 multiplied by delta t minus 5. So this is again very useful result. Next, let me ask another question. Suppose a signal yt is given as delta of some constant k times t. For example, delta of 2t. K is some constant, let that be 2. How will that signal look like? Let me draw that in this way. Delta t is a very narrow spike near the origin, near time t equal to 0. So let this point, although I am drawing it quite large, let this be 0 minus and let this be 0 plus. So I am zooming in near the time t equal to 0. This is delta t, and now if I draw delta kt, this is time scaling of delta t. For example, if k is equal to 2, then this signal will be compressed or squeezed along the time axis by a factor of half. So this will become like this, more narrow, but the height will remain same. This signal is delta 2t, and the area under this curve is, of course, half of the area of delta t. So the area under delta 2t is equal to half. In general, the area under delta kt will be 1 over k. So this signal is therefore again an impulse signal which is non-zero only near the origin and zero everywhere else. But the area under this curve is finite. It is not equal to 1, but it is equal to 2, or it is equal to half, or 1 over k. Therefore, I can write this is equal to half of delta t. Similarly, delta of kt is equal to one over k delta t, and this is again a very useful result that you should remember. I think today we have enough mathematics, enough new and puzzling stuff. So in the rest of the class we shall take up some lighter topic and we shall discuss about systems. In the remainder of this class, we shall talk about systems. But before that, we shall play a game. This is a train simulator. Let me give a name to my train. Call it 21101 up System Express. And I am the driver of this train and you are my passengers. My train is very simple. It has only one control, which is this lever. If I push this lever up, then the train gains speed, and if I pull it down, then the train slows down and eventually stops. So this is the input to my train, and the output from my train is the speed. In other words, the change of position of this lever is the cause of speed change, and change of speed is the effect of varying the position of this lever. Now, my goal in this game is to reach my destination station as quickly as possible. Therefore, I shall push this lever up to the extreme highest position so that my train gets its maximum speed and I shall reach my station as quickly as possible. But soon after, when I see the station is approaching me, then I have to pull this lever down so that the train stops at the platform. However, the train doesn't stop. It continues to run due to inertia, and I encounter an accident. Now I can retry this game and this time I will keep the speed very low so that I can stop the train whenever I want very quickly. But if I keep the speed of the train very slow, then I shall reach my destination station very late. Now this problem arises because I do not know exactly how much to increase the speed and exactly when to decrease it. The relation between this input and the output, which is the speed, is not very well known to me. I do not know very well the relation between the input and the output or the speed, and that's why I do not know how to manage this situation. Now, the input or the position of the lever can be changed with time. As time changes, I can also change the position of this lever or the input up or down. Let me draw a curve where the x-axis denotes time and the y-axis denotes the input to the train as a function of time. Now I can raise this position high at the beginning, and then after a while I can bring it down. As a result, the speed of the train also changes as a function of time. Let me plot another curve where the x-axis is time and y-axis is the speed of the train as a function of time. When I increase the input, the speed also increases, but slowly. It keeps increasing up to this point. When I decrease this lever position, but then the speed does not become zero instantaneously, but it goes down to zero slowly. This is how the input as a function of time and output as a function of time looks like. Now, if I were an experienced driver, if I knew the relation between this input and this output pattern, then I could reach my destination very quickly in the smallest possible time, in the shortest possible time, without making an accident. But since I am not that experienced, I cannot do that. But not only an experienced driver can drive this train well, also machines or computers can drive trains very precisely. Platforms in many advanced countries are secured with screened doors like this, and the train is often driven automatically without any human driver. Such trains which are driven automatically can stop very precisely at the correct position so that the doors of the train and the doors of the platform are perfectly aligned. This is possible even when the train is driven by a computer without any manual intervention. Now think of an aircraft in place of a train. An aircraft is much more complex compared to a train. It has many inputs. You can control the pitch angle, the roll, the yaw with the joystick. You can control the thrust to the engine, you can control the flap position, you can control the rudder position. So it has many inputs. And what is the output? Output is the 3D position of this aircraft in the air. So both the number of input is more than 1 and the number of output is also more than 1. And the relation between the input and output is more complex than a train. However, you must be aware of that often an aircraft can be driven completely with autopilot without any human intervention. That is possible because the autopilot or the computer knows the relationship between various inputs to this aircraft and its output very well. Let us now ask, what is a system? Any object, any machine which has one or more inputs and one or more outputs, that can be considered as a system. We call that a system. A train can be a system, an aircraft can be a system, a car can be a system, where the inputs are the position of the steering, the position of brake, accelerator pedal, etc. And the output of the car is its speed or position or acceleration, etc. A simple motor can be a system. The voltage that you apply to the motor, that is the input, and the speed of the motor could be the output. A generator can be a system, so the speed at which the generator is driven, that could be the input, and the voltage generated, that could be the output. A turbine can be a system. The amount of steam that you feed, that is the input, and the power or speed of the turbine, that is the output. So any machine, any object which has input, output, and some relation between its inputs and outputs, that can be considered as a system. So that is what I said. Any machine is a system. Now, the inputs and the outputs of a machine or a system, they can vary with time. So input and outputs are functions of time, therefore they are signals, and that's why we are studying about signals. Now, to be able to control a machine properly, we need to understand the relation between its inputs and outputs very well. We can often ask questions of the form that given a system, for example our train, and some known input pattern, that is say how I am varying the position of the lever with respect to time. So given the input, how will the output vary? That means how will the train move? So we can ask, if I know the input, how will the output change? Input is also known by the term excitation, and output is also known by the term response. Now I can ask the opposite question, like say given a system like our train, and if we have a desired output, that means if we want the train to move in a particular way, then what kind of input or excitation is required? So given I know how the train should move, how should I control the position of the lever? This is the opposite question. One can also ask questions of the form that can I make a system whose input-output relationship is as I desire? For example, we saw in case of our train, the output or the speed doesn't change instantaneously when I change the input. There was a delay due to inertia. Now can I make a train so that there is no delay between the input and output? Then it will be more easy for me to control that train, and it will be less likely to make fault or accident. All these questions are asked and investigated in the subject called system science or system theory, which is what we are studying in this course. Thank you and have a very nice day.